In this video, we will solve the problems on elastic constants. What are the elastic constants? Young's modulus E, modulus of rigidity G, bulk modulus K, and Poissons ratio nu. These four constants are called elastic constants. So in the previous video, we derived the relation between these four. Okay, just I'll recall. If we want a relation between E and G, that is Young's modulus and the modulus of rigidity, we derived the relation E equal to 2 times G into 1 plus nu. This equation we derived. Okay. If you want the relation between E and K, that is Young's modulus and bulk modulus, we derived the relation E equal to 3K into 1 minus 2 nu. 3K into 1 minus 2 nu. Okay. So if you want the relation between E, G and K and nu, also we derived the relation in the previous video. E equal to 9 kg divided by 3k plus g, right? 3k plus g. So these are important, the relations, and they will help while solving the problems here. Okay. Now we'll come to the problem here. I'll read the problem. When a 12 millimeter diameter specimen, that is a diametrical specimen is there, its diameter is 12 millimeter. Just I'll draw here for understanding purpose. I'll draw here. This is the specimen, solid specimen of diameter. This is 12 millimeter. This is 12 millimeter diameter specimen is subjected to a tensile force of 20 kilonewton. It is subjected to an axial tensile force. It is 20 kilonewton. Okay. This is axial tensile force, outward tensile. A deformation of 0.3 millimeter is observed over a deformation of 0.3 millimeter. It means its change in length. Change in length, whatever it is there, after applying a load, it will obviously changes its shape. Just is final diameter, final length and diameter is like this, right? This is final position. Its change in length, whatever change in length, it is 0.3 millimeter is observed over a gauge length of 150 millimeter. What is 150 millimeter? It is original length. This is original length, gauge length. This is called, that is original length. This will be equal to 150 millimeter. 150 millimeter. And this is force. This will be equal to force. And this will be equal to original diameter. Original diameter. Okay. Reduction in diameter is 0.0079. How much the reduction in diameter? That is this diameter. Obviously, if you apply a tensile load, along the length also it will changes, and along the diameter it will reduces, right? So whatever the reduction in diameter, this will be change in diameter. Can I write it? This one is change in diameter. That is change in diameter. Okay, change in diameter equal to change in diameter equal to how much? 0.0079. These are all the data is given. What we want to find out? Determine, first one is Young's modulus. We need to find out the E. That is, we need to find out E equal to how much? That is the first one, Young's modulus. Second one is Poissons ratio. Nu equal to how much? Third one is modulus of rigidity. What is that? G equal to how much? Fourth one is bulk modulus. That is K. K equal to how much? These are all data we need to find out here. First, we will analyze the problem and we will go one by one the relation. Okay. Just one more time I'll write the data here. 12 millimeter diameter, that is these are the data. 12 millimeter diameter, d equal to 12 millimeter. Specimen is subjected to a tensile force F equal to, along the length, 20 kilonewton. Convert this into 20 into 10 raised to 3 Newton. Okay. Next, a deformation of 0.3. What is that? That is the change in length. Change in length. That is change in length equal to 0.3 millimeter along the axial direction is observed over a gauge length. Gauge length is original length. L equal to 150 millimeter. Reduction in diameter, that is after applying the load, the reduction in diameter, change in diameter equal to 0.0079. Okay, these are all the data he is given. Now we will proceed one by one. How we will start? First, if you want to find out E, what is the equations we can use here? Just formulas we can use here related to E. One, we can use the E equal to stress by strain. Stress by strain. This is one formula. We can use E equal to 2G into 1 plus nu. Suppose if I use E equal to 2G into 1 plus nu, this equation, I don't know the modulus of rigidity because we need to find out modulus of rigidity. I don't know Young's modulus. Okay, and I don't know Poisson's ratio. These are all three unknowns here. So I cannot use first equation here. Okay, and here also K, I don't know bulk modulus, I don't know the Poisson's ratio, and I don't know the Young's modulus. This is also we cannot use. Even third equation also I cannot use. Now normal general formula we will start. E equal to stress by strain. E equal to stress by strain. So I need to find out E. So I will use first E equal to stress by strain. Stress by strain to find out first bit. So what is the formula for stress? Stress equal to load by area. Okay, I will write stress equal to, that is load divided by area. This is stress. And how about the strain? Strain is change in length divided by original length. Okay, change in length divided by original length, right? Strain along the linear dimension we need to consider. So stress is load by area divided by strain is change in length divided by original length. Do we know load here? Yeah, load applied is 20 into 10 raised to 3 Newton. Area is the original area of the solid diameter, pi d square by 4. Pi d square by 4. We know the diameter, 12 millimeter, original diameter. And then change in length, how much? Change in length already is given, 0.3 millimeter. 0.3 millimeter. Next, what is the original length? We know the original length, 150 millimeter. So we can find out E here. Now I'll substitute E equal to load is 20 into 10 raised to 3. 20 into 10 raised to 3 divided by area is, I'll substitute directly all the values, pi d square by 4. Pi into d is diameter. D is pi into 12 square. Pi into d square divided by 4. Otherwise, I will write 1 by, okay. 20 into 10 raised to 3 divided by, else we'll find out 1 by 1 here, load. The stress equal to load by area. First I'll find out load by area. This will be equal to, load is 20 into 10 raised to 3 divided by area is pi d square by 4. Pi into 12 square divided by 4. This will be equal to, so we get 177 Newton per mm square. Okay, this is the stress. Now strain, separately I will find out strain. Strain equal to change in length divided by original length. Okay, so change in length is 0.3 millimeter. This will be equal to 0.3 millimeter divided by original length is 150 millimeter. 150 millimeter. Okay, so this we will get 0.002 millimeter. This is strain. Now substitute stress value and strain value in this equation. Okay, so I will substitute here. E equal to stress is 177 Newton per mm square divided by strain is 0.002 millimeter. After simplification, we will get E equal to 0.89 into 10 raised to 5. 10 raised to 5 Newton per mm square or MPa. That is E value. Because the numerator is Newton per mm square, the stress value, but strain value we don't have any units. So that's why we are getting Newton per mm square. So this is the first bit, Young's modulus we found out. Next, we need to find out the Poisson's ratio. How will go the Poisson's ratio? What is the formula we need to use here? Suppose if we use the first formula, here Poisson's ratio is there. To find out Poisson's ratio, we know Young's modulus. Just now we calculated Young's modulus, but we don't know the modulus of rigidity. It means here two are unknowns, G and nu. We cannot use. Even here, K is unknown and nu is unknown. Bulk modulus is unknown and Poisson's ratio we cannot use. Even this is also we cannot use. Okay. So we have one more equation for Poisson's ratio. The normal equation, Poisson's ratio. What is the normal definition, the general definition of the Poisson's ratio? It is lateral strain divided by longitudinal strain, right? Lateral strain divided by longitudinal strain. This will be equal to, just I'll write lateral divided by longitudinal. That is Poisson's ratio. So we can use this formula. Okay, just I'll solve to find out second bit. Yes. To find nu, that is Poisson's ratio, we'll use nu equal to lateral strain divided by longitudinal strain. Okay. Now we will find out one by one. Lateral strain. Lateral strain. What is the general formula for lateral strain? In the lateral strain, change in diameter divided by original diameter. Right? How much change in diameter divided by original diameter? That is change in diameter divided by its original diameter. So what is the change in diameter is given after applying the load? Change in diameter is 0.0079. Change in diameter 0.0079. It is change in diameter divided by how much is the original diameter? Original diameter is 12 millimeter. Okay. So this is lateral strain. So we will get 0.00066. No unit, because millimeter it will cancels. Okay. So this is lateral strain. Now find out the longitudinal strain. So longitudinal strain equal to, what is the formula? Longitudinal. Change in length divided by original length. Okay. How much the length will be changes divided by with respect to original length. That is change in length divided by original length. This will be equal to, change in length is how much? After application of the load is, change in length is 0.3 millimeter. 0.3 divided by original length is 150 millimeter. This is 150. Now calculate, and after simplification, the longitudinal strain we will get 0.002. 0.002. This is longitudinal strain. Now we know lateral strain, we know longitudinal strain. Substitute in this equation, we will get the Poissons ratio. After substituting this, just substitute. Lateral strain is 0.00066 divided by 0.002. Okay, so this we will get the 0.33 Poissons ratio. That will be equal to nu. Okay, so we use the general formula and we calculated the both values and we substituted and we will get the Poissons ratio. Okay, now we found the Young's modulus and Poissons ratio. Next, third one is we need to find out the modulus of rigidity. So how we will proceed for third one? Can we use any one formula from here? Yes, we can use. See here, we know first equation is E equal to 2 times G into 1 plus nu. We know Young's modulus, already we calculated before. We know Poissons ratio, 0.33. So if you substitute, we can easily use this equation, right? So now third one, we will proceed third one. Third, to find G, modulus of rigidity. So use this equation. E equal to 2G, 2 times G into 1 plus nu. 1 plus nu. So what is the value of E before we calculated? E, that is 0.89 into 10 raised to 5 Newton per mm square. This is Young's modulus, we calculated. Equal to 2 times, we want G, right? We want the modulus of rigidity into 1 plus 0.33. This is Poissons ratio. So after simplification, we will get G equal to, just simplify and we will get G equal to 0.33 into 10 raised to 5 Newton per mm square. This is the modulus of rigidity. Next, third one is finished. Next, last one is bulk modulus, K. So to find out K, which equation we need to use? Where is K? K is either in this equation or in this equation. We can use any one equation. See, suppose if I use first equation, I know Young's modulus, I know Poissons ratio. So I can easily calculate K. So in second equation, I know Young's modulus, I know modulus of rigidity, I can easily find out K. You can use any one equation to calculate. Okay, so I'll use the second equation here. Okay, so fourth one, to find K, that is bulk modulus, we'll use this equation. Okay, E equal to 3K into 1 minus 2 nu, 2 times nu. So what is the Young's modulus value here? That is 0.89 into 10 raised to 5. Already we are calculated, equal to 3. We don't know we want to calculate the bulk modulus K. 1 minus 2 into, what is the Poissons ratio? 0.33. So here only one is unknown data, K, bulk modulus. So simplify, and after simplification we will get K equal to bulk modulus equal to 0.87 into 10 raised to 5. 10 raised to 5 Newton per mm square. Okay, so these are all the values. We found Young's modulus, we found Poissons ratio, we found modulus of rigidity, and we found the bulk modulus. These four are the elastic constants, and this is how we need to calculate all these values here.